everyone. My name is Raman Sridharan. I'm Senior Product Manager at Data Physics, and this presentation is going to be on multi-shaker single-axis control considerations. An overview of this presentation, I'm going to start with a brief introduction on multi-shaker control. I'm going to focus in on the differences between single-shaker control and multi-shaker control, and talk about the complexities of a multi-shaker configuration that single-shaker controllers just aren't designed to control. Then I'm going to focus on actual demos showing a true MIMO control versus a single shaker or a non-MIMO control, and talk about the differences between them and let you see, depending on what your priorities are, why MIMO control might be something you want to look into. Okay, so a brief introduction for multi-shaker control. Why would you need to do multi-shaker single-axis testing? The primary concern in a multi-shaker single-axis test is the test article's geometry and or mass. The structure, for a large test structure, you may or may not be able to excite it with a single shaker. The footprint of your test structure might be too large for a single shaker or a head expander or slip table. You might have insufficient force with a single shaker. Your test structure might be too massive. Or sort of a combination of the two, you might not be able to get a good force distribution between when exciting at a single point or with a single shaker. You might have multiple locations where your structure gets excited from in the real world, and you want to replicate that in the lab, or you just might not be able to get forces and stresses to traverse your whole structure where it's mounted at a single location. So some of the typical applications for this type of test are in the automotive industry with large automotive chassis or large automotive components that are too massive or too large to fit on a single shaker, a typical single shaker, or in the aerospace industry for satellite or aircraft components that obviously can be very large and getting larger as the years go on. Satellites are getting larger and larger, and you need larger and higher force shakers to sufficiently dynamically test those test structures. So some of the complications in a multi-shaker single-axis test. The first complication is that each shaker is going to affect all of your control accelerometers. So a common configuration is a push-push configuration shown here in the bottom left, where both shakers are in the vertical, and your test article or you have a slip table that's mounted, a head expander that's mounted across both shakers, or in this case, your test article strapped across both shakers, test article represented by a simple plastic pipe here. And the common configuration here would be have a control accel here at the mounting location or where your fixture is attached to the shaker, and here. So one control accel on each head expander. And when you run a test like that, driving each shaker is going to cause a response at each of your control accels. What do I mean by that? If I drive the shaker on the right here, I'm going to get a response from the control accel on the left and the control accel on the right. So there's cross-coupling between your two shakers and your two control points. The second point here, off-center masses and overturning moments. If I had more mass on one shaker or an overhanging mass that's going to cause an overturning moment, that's going to mean I need to drive my two shakers differently, sometimes in amplitude and sometimes differently in phase, to account for that off-center mass or overturning moment. Another common shaker configuration is what we call a push-pull configuration colloquially, and that's where the one shaker, it's kind of off camera here, is pushing while a shaker directly opposite is pulling, and the test article is mounted, on top of the slip table or the two slip tables in this case. For this kind of configuration, how do you prevent the two shakers from fighting each other? What happens if this shaker is pushing while this shaker is also pushing? They would generate a force that is equal and opposite and cancel each other out. So how do you prevent that from happening? That can cause a lot of damage to your shaker, your test article, or your amplifiers. if that happens and goes uncontrolled. What about the mode shapes of your table and test article? Once my test article goes into resonance, it's going to try and force my control accels to vibrate out of phase and with different amplitudes. So how do you adapt for that? How does the controller adapt for that? And the last complication I'm going to go over in this presentation is controlling multiple axes at the same time. And this is easily visible in this configuration here on the left, the push-push configuration. What happens if one shaker is moving up while the other shaker is moving down? That would mean that this test article is rotating. And what are the repercussions of that? Why would you want to prevent that from happening? Okay, so that's a brief outline of the complexities in a multi-shaker single axis test. Now I'm going to take a step back and talk about a single shaker controller. So we're going to start out with a single shaker controller, talk about what it does, what its goals are in controlling a single shaker configuration, and then we're going to delve into how, where the shortcomings are in those assumptions made, and why you really need a MIMO controller to properly control a multi-shaker single axis configuration. So single shaker control basics. In a single shaker test, your goal is to reproduce a specific profile, either sine or random or shock, at one location on the shaker or slip table or armature. So for example, if I had my control accelerometer here, and you can see my control accel is going to hit that target reference. But if I had a second response accelerometer somewhere else on the slip table and measure that, the PSD from that response accel might vary quite a bit from the control accel. And in a single shaker control scheme, or when you're driving a single shaker, the rest of the table sort of does what it does, particularly if you're exciting frequencies above the first resonance of your armature or of your table or of your test article. The shaker has one drive, the controller has one drive, and has no ability to control the relative vibration, either in magnitude or phase, of the different points on your control, of the different points you have selected as your accelerometer locations. Oftentimes we'll come in and we'll say, average these two locations so that my average hits my control target. But if you actually plot the individual responses from each of your individual accels, you'll see that they vary. We have no ability with a single shaker controller to control the relative amplitudes or relative phases between multiple control points. So phase is irrelevant, and amplitudes, the relative amplitudes between your control locations, they sort of are what they are. And we're going to kind of see that in the following slides when we show how, when you try to use a single shaker controller to control multiple shakers, we're going to kind of see that pattern over and over again. So as I mentioned before, now I'm going to talk about how various controller vendors try to control multiple shakers in a single axis with what is really a controller meant for a single shaker, right? So when you're running a single shaker controller, the controller has one output variable, the drive signal. It sort of has one thing it can control. And there's various ways that controllers will try to control multiple shakers simultaneously with that one output variable, with that one drive signal. The first and most simplest is just teeing the drive signal into two amplifiers. So for example, take my controller output here, my block diagram, my controller, and if I just took the drive signal and split it and teed it into two amplifiers to drive two different shakers, that's kind of the simplest and most crude way that people try to control two shakers with a single shaker controller. Sometimes if your two shakers are in the push-pull configuration where they're facing each other, they might take the drive and invert the drive, flip one drive 180 degrees in phase, multiply it by -1, feed that into one shaker and the original drive into another shaker or amplifier. And in theory, that theoretically should generate equal and opposite forces. Now in practice, that's not really what happens, and we'll talk about that in a little bit. And the third method that single shaker controllers use to try and control multiple shakers is using some sort of phase matching hardware or phase matching software algorithm, where they'll just invert the drive internally in the controller box, or run the single drive signal into a piece of hardware that will somehow try to match the phase between the shakers. But again, in reality, does not do justice to the complexities of a large shaker system, where there are going to be several, not just a phase offset, but there's going to be phase offsets changing with respect to frequency, and a phase matching piece of hardware cannot properly accommodate those. So in all these cases, the controller has no ability to counteract the complexities of a two-shaker configuration. You're really taking a controller that was designed for a simple one-shaker configuration and trying to apply it to a system or a plant that is much more complex than it was designed for. So what typically happens is you'll take two control points, one control point on each shaker, and you'll control to the average of them like you would in a single shaker test. And what you'll see is if you actually plot the individual responses from each of your individual control accelerometers, they're going to vary wildly from what the average is. So phase matching or changing and inverting the drive signals produces subpar results, even if you have the same model shaker, the same model amplifier. There are always going to be physical differences that end up causing control deviations when you're trying to use a single shaker controller that just wasn't designed for this complex of a system. So some common trade names for single shaker controllers masquerading as multi-shaker control is dual loop or multiple control loops, one control loop per shaker, requiring some sort of phase matching hardware or phase matching in the controller that's going to just invert that drive phase or somehow otherwise phase match the two drives that are going to the two shakers. A system that requires matched shakers. So sometimes the controller vendors will just throw the problem entirely at the shaker manufacturers and say, yep, the shakers have to be perfectly matched, otherwise we can't control them. And what that means is the controller just wasn't designed to control two shakers if you require the shakers to be matched. And as I mentioned earlier, it's damn near impossible to have two large shakers that are actually perfectly matched because just how complex of a machine a large shaker is. Or just the last technique that is very commonly used is just teeing the drive or splitting the drive and setting the same drive signal into two different shakers, two different amplifiers. So there's various techniques. These are the various techniques and sort of the trade names that are given to those techniques in which single shaker controllers are used to try and control a complex multi-shaker single axis test. And now we're going to kind of go into a little more technical details and understand why the single shaker controller is not able to adequately control a multi-shaker single axis test configuration. So the complexities we're going to delve into are the first, coupling between the two shakers or multiple shakers and responses. We're going to focus on a two shaker example, but the concepts fully extend to multi-shaker single axis, 3 or 4 or more shakers in a single axis. We're going to talk about off-center masses, overturning moments, shakers fighting each other, the effects of modes and resonances, and how to control or null, about controlling or nulling rotations when you've got two shakers in a push-push configuration. So starting with the coupling between two shakers, the fundamental problem with using a single shaker controller on a multi-shaker single axis test is that it does not account for cross-coupling between two shakers. And what do I mean by that? If I drive this shaker on the left, I'm going to get a response from my control accelerometer on the left, and I'm also going to get a response from my control accelerometer on the right. That response is going to be different than the response I get on the left. And vice versa, if I drive the shaker on the right, I'm going to get a response from accelerometer 2 and accelerometer 1. Now, if I had one control loop running on this left system, trying to control this accel with this shaker, and one control loop running on the right with this shaker, trying to control this accel, essentially the vibration from this shaker on this accel and this shaker on this accel is going to just be noise on the system. I'm going to end up with some poor control results. My controls aren't going to be able to hit my tolerance bands because it's not accounting for that cross-coupling between each shaker and each control accel. So you really have to treat the system as a MIMO system, as a two shakers, two control system, instead of as discrete individual shaker systems. Now, what happens if my mass isn't perfectly centered, or I've got an overturning moment on my on my test structure here, on my head expander or in my test configuration. So if I had, for example, teed the drive signal from my single shaker controller into two shakers and drove them, obviously my shaker on the left, my accelerometer 1, is going to produce much less vibration than my accelerometer on the right. So with the non-MIMO controller, I'm going to end up with very different levels on the left and on the right. And depending on how far offset this mass is, if the mass was overhanging, the test structure was large and overhanging, and the center of gravity was farther and farther away from in between the shakers, I might actually have to drive these shakers completely out of phase to generate perfect translation up and down and get these two accels moving in phase. So driving with the same signal, splitting the drive with a non-MIMO controller and driving two shakers with the same signal is just not an adequate way to properly control this type of shaker system. Now moving on to the problem of shakers fighting each other. This is most common when I've got two shakers pointed at each other in a push-pull configuration. So for example, I've got shaker on the left and shaker on the right. Now, what happens if this shaker is pushing? So this shaker is pushing to the right and this shaker is pushing to the left. They're going to output an equal and opposite force and cancel each other out. What am I going to see from my feedback sensors? Nothing, because the vibration is going to cancel itself out. The forces are going to cancel out, and the net vibration is going to be nothing. And now, the common thinking would be, oh, let me just put an opposite drive, a negative drive into one shaker, a negative drive into the other shaker. Again, that assumes the shakers are perfectly matched, that your shakers are 100% identical, which is never really the case. I've worked on shaker systems that the manufacturers said were 100% identical, and we should be able to get the same output force by driving them exactly the same way. And in practice, we found that we had to drive them almost 45 degrees out of phase for them to get the same vibration at 5 hertz. And of course, that 45 degrees, that phase angle, that phase offset between the two shakers, that changed as we swept in frequency. Right, so that underlying assumption that you can just flip the drive and you'll get equal and opposite forces out of your shakers, that doesn't really exist in the real world. Now, on top of that, the amplifier dynamics, the device under test, your modes, all form the complex impedance that the shaker sees when it's trying to move, and together will change that relative phase, the phasing between the two shakers, the way you need to drive them to make sure they don't output a force that's going to cancel out. Driving the shakers with out-of-phase signals will not be sufficient to prevent the shakers from fighting each other. Now, shakers fighting each other is a big concern. If you can easily damage, you can get a lot of current going through your shakers with no vibration being detected at your control accels. It's a really easy way to burn out an amplifier or to damage a shaker. Now, what about the effects of resonances? In drawing, I'm showing a solid block as your slip table, but once you hit your first mode of your head expander, once you hit the first mode of your head expander or of your test article, there's going to be some relative motion and deformation of your slip table or of your head expander, and your control accels are going to try to move out of phase with each other. Naturally, even if the shakers output the same force, you're going to get different responses at different locations. So this is where, even if you can have some piece of phase matching hardware that's able to phase match the systems at low frequency, at 5 hertz or at 10 hertz, as you sweep in frequency and as you hit your resonances in your test band, that phase matching piece of hardware is no longer going to be accurate. Or as you hit, if you have some phase matching algorithm running on the output channels that's inverting the phase or doing something to try and keep the shakers in phase, unless you're doing true MIMO control where you're measuring the MIMO, the response from both shakers on both accels, driving the shakers with the same phase matched signal with some sort of phase match signal is not going to effectively control the setup past your first resonance and above your first resonance. Now with multi-shaker single axis, we're really talking about testing larger and larger test articles, right? Large test articles or massive test articles that don't fit onto a single shaker. So this is a big problem because you are going to have resonances in your test band. You're testing larger test articles. Resonant frequencies are going to be low. So this is going to be a problem when running multi-shaker single axis testing. Now, oftentimes, single shaker controllers, non-MIMO controllers will just average control and just show you the average, and it looks like the average looks good. So you think your two control points are in control, and that's not the case. It's the average of the two that's in control, in tolerance. So we're going to take a look at that with some examples here. But the last complexity that I'm going to talk about, that I'm going to touch on, is rotations. The most common configuration, the most common desire in a multi-shaker single axis test is to produce pure translation, to just test your large, massive test article in one axis at a time. I want to excite it up and down, or if your two shakers are pushing on a slip table, I want to excite it in that one axis. But what would happen if your shakers end up moving out of phase because you're not using a controller that properly compensates for it? Well, there's two potential problems here. The first is if your shakers are rigidly coupled to your head expander or to your test article, you could really risk damaging your shakers. You could really risk damaging your armatures. You're going to be twisting and bending your armature here, or your slip or your head expander here, right? If those two shakers move out of phase at low frequency, you're going to cause a lot of stress in that armature and potentially break something in your test system. The second big concern here is if you're testing something sensitive, if you're testing a one-of-a-kind test article or a very valuable test article, typically some sort of satellite, these rotations are not controlled. In a single shaker, when you're running a non-MIMO controller, these rotations just happen. It's not that the controller's controlling them. They oftentimes don't even measure them or quantify them, but they're there, and you can easily result in an overtest because you're exciting your test structure both in the vertical axis here, but also exciting with a rotational degree of freedom when the shakers move out of phase. So by not controlling rotations, you're risking damaging your shaker, head expander, amplifier structure, or shakers and head expanders, and you're risking overtest if you're testing a sensitive test article. Overtest is a big concern, and you're basically leaving rotations uncontrolled. So there's two very big reasons why rotations are important to consider, and a non-MIMO controller just does not consider rotations as part of the control loop. So we've gone over the different technical complexities, the reasons why non-MIMO controllers or single shaker controllers that are used as if they were a MIMO controller for a multi-shaker single axis test. We've gone over the technical shortcomings of those controllers. Now we're going to actually see it in action. I'm going to compare a MIMO controller versus a non-MIMO controller. Now I'm going to introduce a sort of a grid of priorities that kind of, depending on what you're testing, depending on the type of test articles you're testing and the size of test articles you're testing, one of these priorities is going to be your driving force behind doing a multi-shaker single axis test. And then we're going to go through, compare the single axis controller, the non-MIMO controller, with the MIMO controller, and see how those different priorities are affected or improved when you use MIMO control. Now I'm going to focus on a single shaker with a T drive, which is, again, a very common way that is used to try and synchronize two shakers, and compare that to a MIMO control configuration. So the different priorities I'm going to focus on, the first priority is keeping a single location or an average of two locations in control. Oftentimes you're trying to get, if a single shaker doesn't have enough force, you're testing something very large, you really want to minimize the required force to run your test. Or in other words, if you're using two shakers, you want to get double the force out of it, or optimize the force output of your two shakers. Sometimes your key concern is to keep two locations in control. If you want your two mounting locations on your where your test structure is mounted to the shaker to be exactly in control, maybe that's your concern, is keeping those two mounting locations in control. Your concerns might be handling cross-coupling. You want a controller that's going to properly and adequately control all the variables in your test. Perhaps handling off-center masses, or another problem, using amplifiers or shakers that are not identical, that are not mechanically identical and electrically identical, well, in that case, you're going to need a controller that's going to be able to handle that. If you're concerned, especially if you're using a push-pull configuration, preventing the shakers fighting each other should be a pretty big concern of yours. You want to make sure those shakers don't fight each other and risk damaging your amplifiers or burning out an armature. Perhaps controlling or counteracting resonances, structural resonances, is of concern to you. You want to be able to make sure that structural resonances don't affect your control tolerances and your control points stay in control. And the last item here is controlling rotations. You want to make sure there's no relative motion between your armatures if your shakers are rigidly coupled to the test article, meaning you want to protect your shakers and armatures from damage, or you want to protect your test article from overtest. You don't want to have uncontrolled rotations on your test article. You don't want to impart uncontrolled rotations into your test article when you're just trying to test it in a translational axis. Okay, so these are the different priorities that may or may not be of concern to you. So kind of delving into that, which of those priorities should be of concern to you? And again, this depends on what type of products you are testing. So controlling to a single point is of concern to you. You just care about the energy at this one location. I want the PSD at that one location to hit my target profile. Well, then keeping one location in control and being able to handle cross coupling, which is going to affect your ability to keep multiple locations in control. That might be the concern in your world. If you're testing large or massive test articles and you want to maximize your available force in your system, then minimizing the required force for a given profile is of concern to you. If you want to make sure that your shakers, the locations where you've mounted your test article, have the same vibration level, or think of that as the input vibration to your test structure, you want those input vibrations to be uniform or to have a uniform vibration field, then keeping multiple locations in control, counteracting off-center masses and differences in shakers and amplifiers, and controlling and counteracting resonances are all going to be of concern to you. If protecting the shaker and test system are of concern to you, then you want to make sure that your shakers don't fight each other. That puts your amplifiers and armature coils at great risk. And you want to make sure that you're able to keep your two armatures in phase. Keeping multiple control locations in phase is a concern if your shakers are rigidly coupled to your test system, to your test structure. If you're testing satellites or other valuable test articles, then preventing overtest or controlling and nulling rotations is obviously a huge concern to you. Okay, so we're going to go through and kind of show how a non-MIMO control, splitting the drive off of two different shakers, two different amplifiers, behaves differently than the MIMO control case. So we're going to kind of fill out this grid, this table here. Now, the system I'm going to be testing on is shown here. I've got two shakers, the shaker on the left and the shaker on the right, and I've got two control accels that I'm using, labeled A1 and A2 here and here. Okay, across the two shakers, they're rigidly coupled with a L bracket that has several modes in the test band. So we're going to see lots of cross coupling. We're going to see the effects of resonances, and we're going to look at how the single shaker control versus the MIMO control can effectively control the system. So the first example I'm going to do is I'm just going to do the most common method. I'm going to do T the drive to my two amplifiers and look at the control results. So to run this test, I'm going to start with my controller configured, my test setup configured as a single shaker controller, and I have my drive teed to both my amplifiers. So the drive signal is teed to both amplifiers and both shakers. And then I have both of my control accels set to be average controlled. And we're going to see what happens here. So let me initialize my test and start my test. It's going to run through the self-check. Go into my pretest page. So my self-check is running. I'm outputting one drive signal that's being split to two shakers. So as far as the controller knows, I'm connected to one shaker. And I hit start test. So I've got my control plot at the top and my drive plot down at the bottom. And now in the interest of time, I'm just going to bump the test level up a little bit more rapidly to get up to level and take a look at how the control looks. So the average control looks good. The average is sitting right on top of the control line, on the reference line. But if I were to go and take a look at a plot with my two individual control channels, so the left and the right control accels plotted in blue here, the average is in red now. The two controls are doing something pretty wildly different. Down at low frequencies, they're behaving differently. And then at higher frequencies, where I have a lot of modes in my test structure, they deviate quite a bit, even though the average looks good. Okay, so that's the end result. There's not really any, aside from moving your control accels and playing some games with the gain on the amplifier, there's not a whole lot you can do to really improve this with a single shaker controller controlling both shakers. So if I come back to my grid, the non-MIMO controller is able to keep one control location in control. Let me come back and run the same test with a MIMO controller, with a controller configured in a MIMO configuration. Let me go in and open up my MIMO test configuration. I'm going to be running the same profile, same control channels, but instead of averaging, obviously I'm going to do a MIMO control on the two. Reconnect my drive signals, so I have two independent drive signals instead of one teed drive signal. And my amps are gained up, and let me start the MIMO test. So start. My pretest is running. Now the pretest is fully quantifying all the cross coupling here. You can see multiple frequency response functions between each shaker and controller. And now I've got a pretest report that tells me exactly how much I'm expected to see in how many drive volts and how many Gs I'm expected to see for each shaker and each of my control accels. Start the test. All right, and again, in the interest of time, I'm going to bump up the test level a little bit more rapidly to get the test up to level. All right, so here we are at 0 dB with the same profile, quarter of a G RMS. And you can see my two control lines are actually right on top of each other. It's kind of hard to tell the two apart. Down below, you can see I have two independent drive signals that vary slightly, but that slight variance in the drive signals is what's allowing me to keep both of my control points exactly in control. Okay, so coming back to the MIMO control, both the individual control channels, and so obviously their average, lies right on top of the reference line. Compare that to the single shaker control, where the average was on the line, but the two independent individual control channels were doing something wildly different. Okay, so the priorities grid, I can fill in a little bit more. Handling the cross coupling, so obviously keep one location in control. MIMO had no trouble doing that. Keep two locations in control. The MIMO controller had no trouble doing that, and the single non-MIMO controller could not do that. Now, how does it do that? Well, it's handling all the cross coupling between the two shakers and the two control accels. So the MIMO controller gets a check for that, and the non-MIMO controller does not. So our next consideration we're going to look at is to simulate an offset mass. So what happens if your mass is offset from the center? So you don't have a perfect system anymore. So to simulate an offset mass, I'm just going to turn the gain down on one of my shakers. So I turn the gain down on one of my two shakers. Now, I should also point out that this is also just a realistic configuration where you have two shakers that just aren't perfectly matched. Again, no two shakers are perfectly matched, but if you have two shakers that are wildly different, then yeah, having a different gain between your two shakers is simulating that, having two different shakers. All right, so let's take a look with the T drive. I've reconfigured my drives, reconnected my drives, and let's take a look at how the T drive handles the case where the gains on the shakers are slightly off, or where we have an offset mass. run the pretest. We're outputting the 1 drive to 2 shakers. The pretest is running. And let me, again, in the interest of time, bump up the test level. All right, so we're at 0 dB here, and you can see the average control looks good. But when I look at the 2 individual control channels, they vary quite a bit. And one is, even at low frequency, one is quite a bit above the control line, 3 dB above the control line, and one is well below the control line. So that's, again, what's going on there. Stop and end and go back to my PowerPoint. So what's going on here is I've got my shaker on the left that has a lower gain. That's moving a little bit. And the shaker on the right that has a higher gain is moving a lot. The average of the 2 accels is hitting our target. But this offset mass, or this change in gain, is causing the 2 individual control accels to deviate quite a bit. So again, a case where you have a test article that's not perfectly, where the mass isn't perfectly centered, that's going to cause control deviations between your 2 control points if your test structure, if your moving mass is not perfectly centered. So let's take the same case and fill in the gain off-center mass gets an X for the non-MIMO control. Now let's look at the MIMO control with the offset mass. So let me reconnect my drive signals. So I have the independent drives going to each shaker. Gain on my shakers, my amplifiers, and let me run my MIMO test with the same configuration. So I'm running the pretest. Right, so the self-check is going. All right, so let's start the test. Again, in the interest of time, I'm going to bump up the test level. And you can already see that the two individual control accels are doing a much better job. And if we look down at the drive levels, the drive signals, we can see that, yeah, they're pretty different. It's driving the two shakers with quite a different drive level in order to make sure that the two control sensors are moving exactly the same. So it's counteracting for those offset masses, for the gain differences in the shakers. We can see that the MIMO case kept all the control points, both the control points in the control, and with the non-MIMO case, they deviated quite a bit. So our complexities grid, MIMO gets a checkbox for handling off-center masses and differences in the shakers and amplifiers. All right, so the effective resonances. The next complexity we're going to look at is the effective resonances. Let's see what the T-drive system does when we're running with resonances in our test band. So let's, instead of rerunning this test, let's look at the data from the first experiment, and let's open up that data in review mode in the software, the 900 series software. Go to my first run and open it up in review. And let's take a look at the control channel deviation. So we saw at low frequency, below resonances, we had differences in the amplifiers that were causing some control deviations. Now, after the first resonance, you can see that the control channels are never converge, never identical, except for some places where they kind of switch between one being higher and one being lower. So this is the region where I have resonances in my test band, and you can see the two control channels are deviating a lot. And just in general, with a single shaker controller controlling the system, there is no way to keep these two control points in control past your first resonance. So if these two control points were your mounting locations where your test article is mounted, there's no way to make sure that that input vibration is the same to your test article at both the mounting locations, because the single shaker controller doesn't have any way, the non-MIMO controller doesn't have a way to keep two test points in phase or with the same relative amplitude. Okay, so coming back to our complexities grid, controlling resonance gets an X for non-MIMO. Now let's take a look at data from the second run, the second experiment, where we had resonances in our test band, and we can clearly see, yeah, the two resonances did not cause any deviation, or the several resonances didn't cause any deviations between our two control points. So comparing the MIMO to the single shaker controller non-MIMO case, you can see the MIMO case provides a very uniform control even when we have resonances in our test band. So it's able to counteract that. So MIMO control takes into account the structural resonances and the relative amplitudes between your control points. All right, so let's say you have a test article that's too large for a single shaker. You need more force, and you want to use two shakers to test your test article, and you want to get the most force out of your two shakers. So let's look at using a T-drive method to control that. So I'm going to turn my amplifier gains back to their normal level and flip the drives back to T, the drive, one drive to two shakers. And let's run our control software with the T drive looking at the drive levels. So let's say my goal again here is to maximize the amount of force I can get between my shakers. So the T drive method, looking at my amplifiers. All right, so we're going to start the test. I'm going to bump it up to level. And as we know, the two individual control accels are not going to be in tolerance, but the average of them is. And if we look at the drive level, it's about 11 millivolts of drive going into each of the two amplifiers. Okay, so we've got 11 millivolts of drive to get the average control of the two control channels within tolerance. Okay, so let's take the same test and run it with a MIMO configuration. So let me go back, open up my MIMO configuration for this test. And let me reconnect my drive BNCs. I've got two unique drives instead of the one. And let's run it with MIMO. Now I have to point out that this MIMO test is configured to minimize the drive. There's a way the MIMO test can use all of that MIMO data and minimize the overall drive level that it needs to drive both the shakers with. And what that does effectively is maximize the amount of output force you can get between with your two shakers, and does that by ensuring that the two shakers aren't fighting each other. So it's using all the data it collected from the pretest and the test to decide in what way I need to drive those two shakers to optimize the output and get the most out of my shakers. So if your goal here is to get the maximum amount of force you can possibly get out of two shakers, we saw how much drive voltage this test required with the non-MIMO case, with the single shaker controller controlling it. And with the MIMO controller, you can see it's a little bit less, 10 millivolts, 9.3 millivolts versus 11 and 11. And added bonus, I'm getting much better control. Okay, so my controls are both right on the control tolerance. And if I compare the single shaker case, the single shaker control case to the MIMO control case, you can see I had 11 millivolts and 11 millivolts in the single shaker control versus 10 and 9 millivolts in the multi-shaker, in the MIMO control, and I have much better control. My two control points are both operating well within tolerance. Okay, so in the MIMO case, if your goal is to optimize the amount of force you can get out of your shakers, MIMO does a much better job of that than single shaker control, all while still getting improved control. Okay, so filling out the complexities grid, minimize required force for a given profile. We're both running the same profile, but the MIMO control does a better job of controlling it with less force requirement from your shakers. All right, for the next point, preventing two shakers from fighting each other. This is a big concern in protecting your shakers and protecting your amplifiers. You want to make sure that your shakers are not outputting drives or that your controller is not outputting drives that's causing the shakers to fight each other. So in order to demonstrate this one, since this happens more in a push-pull configuration, I have data from a previous test I've run where I had my two shakers flipped in the horizontal, pushing and pulling on a slip table with some ball bearings in there to allow the slip table to move freely back and forth. So I'm going to take a look at the T drive. I had one drive inverted, flipped 180 degrees, go into one amplifier, and the normal drive go into the other amplifier. And let's take a look at the control results and see how the test ran in that configuration with the T drive or inverted drive. This is that test data. So you can see my drive, my control profile, the red average is right on the line, right on the money. My control deviates slightly. This is kind of where I had some control problems because of some structural resonances. And overall, my drive level was 27 millivolts RMS going into each of my two shakers. So 25 millivolts and 25 millivolts. Now let me bring up the data from the MIMO version of that test, where that test was run with a MIMO control. And first off, we can take a look at the two control channels, and you can see that they are much better within tolerance, much closer to tolerance. Looking at the drive levels now, it's 12 millivolts and 5 millivolts instead of 27 and 27. So let me bring back up my PowerPoint. I've got the two side by side. You can see my control was better in the MIMO case versus the T drive case. And my overall drive level, 12 millivolts and 5 millivolts versus 27 and 27. So the T drive case had 300% more energy. And all that energy is just the two shakers fighting each other. One shaker pushing, both shakers pushing, or both shakers pulling at the same time. Now, if this goes uncontrolled, this can easily cause damage to the shakers or the amplifiers. And I don't notice anything from my feedback sensors. My feedback sensors don't give me any indication that that's happening. All right, so the controller actually has no way, if you're using a non-MIMO controller, it actually has no way of knowing whether your shakers are fighting each other, let alone the ability to compensate for it. Okay, so preventing shakers from fighting each other, the non-MIMO controller, not able to do it. The MIMO controller is kind of baked into the algorithm. All right, so the last and final technical challenge I'll talk about here is controlling or nulling rotations, which is of huge concern if you're testing satellites or testing high-value test articles where you need to prevent overtest, because rotations are an additional degree of freedom that a non-MIMO controller wouldn't just ignore and just not control. It's uncontrolled. So that can easily cause an overtest. Even if both your control PSDs are in tolerance, might not even be measuring the rotations imparted to your test article. Now, if your concern is protecting your shakers system, if those two shakers move out of phase and cause a rotation at low frequency, that could cause damage to your armatures and to your head expander. So keeping the two control locations in phase or keeping nulling rotations should be of concern to you if your big concern is to protect your test system, your shakers. So let's launch the control software again, and with the T drive method, let's look at how the rotations behave when we're controlling with the T drive. So let me reconnect the drives to the same output channel, gain up my amplifiers. All right, so I'm going to run this test with the T drive. Self-check. All right, and what I have here down at the bottom is I've actually plotted the rotations. I actually have a math channel that's computing the rotations from the two control sensor locations at the left and right side, and it's computing that in the time domain and the frequency domain. So I can take a look in the time domain and frequency domain as my test gets up to level. Bump it up to 0 dB. All right, so my control is at 0 dB now. My level's at 0 dB, and I can see that my rotations are 12 radian per second squared RMS. In the time domain, you could see it's about 35, 40 radian per second squared peak. So that's that's completely and entirely uncontrolled, right? So this could result in overtest if you're testing, if you're in the aerospace world where overtest is of great concern to you. This scenario is one you want to avoid. So let's stop and end that. And let's reconfigure 2 independent drives and run this in the MIMO configuration. My 2 drives, gain up my amps. I'll start my MIMO configuration. All right, start my test. And let's take a look at the 2 rotations as my test comes up to level. The frequency and time domain of my rotations. So you can even just take a look at the scale on the time domain plot. It's much, much lower. So we're looking at about 0.5 radian per second squared RMS when I'm actually controlling the rotations out with MIMO versus 1.0, 1.5 peak in the time domain when I'm actually controlling out the rotations with MIMO control versus with the T drive single axis controller. The T drive method resulted in 12 radian per second squared RMS, or about 36 to 40 radian per second squared peak in the time domain of angular rotation. And the single shaker controller could not control those rotations. And oftentimes, as I mentioned, it won't even be calculating them. Now, if the profile had significant energy at low frequency, then rotations can cause your shakers to move out of phase, and rotations would mean your shakers are moving out of phase, and you can cause a lot of damage to your armatures or head expanders. If you're testing a high value test article, this additional 36 radian per second squared, it can result in an overtest scenario. Okay, so the non-MIMO controller, not able to cancel out rotations and not able to protect your shaker system from the shakers moving out of phase with each other. And in the MIMO case, we see very low rotation, 0.5 RMS, 1.5 radian per second square peak. So we're able to protect the shaker system and prevent overtest from uncontrolled variables, uncontrolled degrees of freedom that are present in our system. So using MIMO control is really necessary when testing sensitive test articles in order to prevent overtest. Right, with a single shaker controller, you don't have any ability to prevent those rotations from happening. So coming back to our complexities grid, the MIMO controller has all of the capabilities here to control, prevent shakers from fighting from each other, and to keep rotations, to null out rotations and keep your shakers moving in phase. Okay, so in summary, regardless of really what your goals are in running a multi-shaker single axis test, whether you're interested in protecting your shakers and amplifiers, you're interested in producing a uniform vibration field so you have the same vibration at multiple locations where your test articles are mounted, whether you want to prevent overtest for a high value test article, across the board, the MIMO controller really does the best job of both protecting your test article, preventing overtest, preventing your shaker system from damage, your amplifiers and shakers from damage, and just overall of keeping a uniform vibration field across all of your control points. Okay, so I've gone over a lot of very technical details at a high level in this presentation. If you want to learn more about how MIMO control can optimize your multi-shaker single axis test configurations, please feel free to view these links on our website, or you can reach out to me at raman.sridharan@dataphysics.com, and I'd be happy to talk in more detail with you about your specific test configuration. So thank you for watching this webinar, and have a good afternoon.